Okay, hi everyone. So as you know, we are starting this review from today's lecture and then on Friday also, and Monday and Wednesday. So we will have 4 review hours. I highly recommend you look at all sections. Well, every section could be part of exam actually, but I said that the emphasis is on latter parts of the text. So what we covered after midterm. But nevertheless, we can start from beginning, from the idea of vectors and all that, or we can start from any section you want. So who is going to ask the first question? So no questions at all? Okay, so I can maybe start asking some questions myself then. All right, so let's just start from right from beginning. One of the things was, well, maybe not right from beginning, maybe from section on multivariable functions, differential calculus, and all that. So one of the things you remember, we have this chain rule. So do you have any questions about chain rule? You can open your books, PDF files, and look at the section on chain rule and ask me some questions. Okay, so there are no questions, so let me continue then. So the idea of chain rule, so let me give you an example. So one of the examples where it could be something like this. We have functions like that x equal to r cosine of theta, y equal to r sine of theta. So this is a transformation that sends a function in our theta variables. We don't care about the geometric meaning of r and theta at this stage. So these are just two variables for us, right? R and theta. And so this map takes us to xy plane. So it's given by this. So if you know some point here which has coordinates, say r and theta, then it comes to a new point here with a totally different coordinates, which are x and y, and they are given by this formula. Of course, I chose a function which is I mean, set of functions that are very well known. This is, do you know what is the importance of these functions? So these are polar coordinate transformations, of course. So now let's assume you have a function. So now you have a function of two variables. These variables are x and y, which is of this form. For example, this function is given by x over x2 plus y2 plus xy over x2 plus y2. So as you look at it, it's a function of two variables, x and y, right? So we can replace x and y by r and theta, and then f becomes a function of r and theta. So this would be f of x of r and theta and y of r and theta. So the picture we can have in mind is that there is this map F that comes to one-dimensional space R. So we are composing this map with this map. So we get the function sending r theta values to R. Originally, the function was sending xy values to R. So we just compose. Okay, so what is the question now? The question is, we want to find the derivative of this new function with respect to theta. Find df d theta df dr, and also maybe d2f dr2, second partial also. Okay, so how we are going to do this problem using chain rule, sorry. So the chain rule says that the partial derivative of this function f with respect to r with respect to r is obtained like this. You take partial derivative of x with respect to x, of f, I mean, with respect to x, times partial derivative of x with respect to r, plus, and then we have to do partial derivative of f with respect to y times partial derivative of y, again with respect to r. So as I emphasized in class, it's kind of useful to have some sort of checks in place so that you make sure that you haven't made some outrageous mistake. In this case, the check, a quick check is that you kind of cancel informally. I mean, this is not a real cancellation because this is not quotient of two numbers. This with that, and you end up with the FDR. So basically, on the right-hand side is of the form dFdr, and left-hand side is also of the form dFdr. So at least the initial check works. I mean, this is not a proof that this is correct, but you know that you haven't made this outrageous mistake. Otherwise, it's okay. All right. So now what we do? So the f dx is very easy. The f dx derivative of this guy with respect to x. It's actually not very easy. It's it involves some calculations. So let me put it like x over x2 plus y2 plus xy over x2 plus y2. I just write it like with respect to x times dx dr. Dx dr is not so bad. It's cosine of theta. Plus So next one is df dy. Here df dy, so this is same thing, x over x2 plus y2 plus xy over x2 plus y2 with respect to y, we have to take the derivative of this guy with respect to y, times dy dr. dy dr is sine of theta. The sine of theta. All right? So now, we are not done, of course. We have to take derivative of this still with respect to x and derivative of this guy with respect to y. So this is kind of longish here, but let me just quickly do at least part of the problem. Otherwise, we have done everything. So this is like x over x2 plus y2. So now we are computing this derivative. So it's this one, x over x2 plus y2 with respect to x plus xy over x2 plus y2 again with respect to x. Both of them are with respect to x. So let's continue. This is equal to, now with respect to x, derivative of this is 1 times x2 plus y2 minus derivative of this guy with respect to x is 2x times x minus 2x squared, right? Divided by x2 plus y2 squared. And remember, we are just computing these parts now. Okay, so this is what? This is equal to x2 minus y2 over x2 plus y2 squared, right? Okay, so that's, now we are done with taking this derivative with respect to x. You have to take this derivative with respect to y and then multiply. So now at the end, we have to replace x and y by the values that we got here. Just this part, again, I'll just continue with this part. We do get, indeed, in this case. So I'm just continuing from here. X2 is R2 cos squared of theta minus R2 sine squared of theta divided by x squared plus y squared. If you compute x squared plus y squared, you get R2 because this is R2. And R2 cancel, so you get equal to cos squared of theta, right? Minus sine squared of theta. So this is the cloud here that goes here. And then we have to multiply this point by cosine of theta. So you repeat the same sort of calculation with this part. Now, can you tell me what is the value of cos squared of theta minus sine squared of theta, by any chance? So I got an answer. That's good. Cos of 2 theta. Yeah, that's yes, that's absolutely correct. Thank you. Yes, this is equal to cos of 2 theta. So at the end, this part, the first part, becomes cos of 2 theta times sine of theta. So the first part of the final answer is going to be like this. Times sine of theta. Now, we are not done, of course, so you still have to do this, times cosine of theta, sorry. So we have just calculated half of the story now. And then you have to do the other half. I don't do it because it's completely similar. So you just have to calculate with respect to y. Now, the point is that at the end, you have to write everything in terms of r and theta. There shouldn't be any values of x and y in your final answer. So if in your final answer you give me x and y values, that cannot be correct. You have to write everything in terms of r and theta. Okay, so there is some, okay, this was the answer. Okay, that's good. Okay, so there are no other comments. Good. Okay, any questions about this? Yeah. So this is one typical example of chain rule. You have a function of several variables. Each of those are functions of some other variables. You sub in, and then you get a function of these new variables, and the question is to compute the derivatives. And there is some rule which sometimes we want to compute partial derivatives in an implicit way. So let me put it like this. Given the relation f of x, y, z equal to x2, y2, z2 plus x, y, z plus 3 equal to 0, given that that guy is equal to 0, right. So given that this is equal to 0, so the question is find dx dy and dx dz. So this is the issue of finding partial derivatives by an implicit calculation, right? So we are computing this partial derivative in an implicit way. So this is implicit partial differentiation, for example. So what is the logic here? The logic here is that, okay, because f of x, y, z is equal to 0, because there is a relation, these three variables are tied together, they are not free. There is a question again, it seems. Okay, so let me get my glasses. Oh, it's here. So the question is, why is the chain rule a sum? Well, the chain rule is a sum because the variations of these things, the chain rule that you have seen in one variable case, that was just one variable case. That was calculus 1000 chain rule. That was the original chain rule. But this one is the multivariable chain rule. So there are functions of 2 variables. So there's going to be 2 terms. Function of 3 variables, there's going to be 3 terms. Because each of these terms can change. F can change with respect to R, can change with respect to X. And F can change with respect to X, and we can change with respect to Y. So you have to be aware of that. There is a proof for it in the textbook. That's also true, yes. Okay, that's good. So now, okay, here we have got f of x, y, z equal to 0. As we were discussing, from here you can find, you see, these 3 variables are tied together. So if you give me values of y and z, I can go and solve this for x. So I can say x is equal to a function of y and z, for example, like this. So once you see that x is a function of y and z, maybe you just write f of y and z. It's a function of, no, not f, maybe g of y and z. Then the question makes sense to talk about partial derivative of x with respect to y and partial derivative of x with respect to z. Because after all, x is a function of y and z by this relation. But of course, you can turn around and say that y is also a function of x and z. And z is a function of x and y. So you can have dependence of any of them on the other 2, on the remaining 2. So you get functions like that, right? Okay, so in this case, we are assuming that x is a function of y and z, and we want to compute. Then we just have to, so let me give you the rule now. So let me give you the rule. So f of x, y, z equal to 0. So what we can do, we can take derivative of this guy, for example, with respect to x. I mean, derivative of this with respect to y and with respect to z. I mean, we just write f of, because x is a function of y and z, we can just maybe secretly write f of y and z, and then y and z equal to 0. Let's take partial derivative with respect to y. So what we are doing, we are taking d dy of both sides, right? D dy on both sides. I mean, it has to be 0 because, I mean, as a function of y and z, this is identically equal to 0. This is an identity, right? So you get that df dx times dg dy plus df dy equal to 0. This is a crucial relation that we always use. But you see, if you want to memorize these formulas just the way they are, you run into difficulty because either you must have huge memory, it's better to spend it on more useful things. Well, I mean, having a good mark in exam is an extremely useful thing, of course. But I mean, even preparing for the exam, perhaps you want to. This, you don't have to memorize anything. Everything follows from first principles. That's what I'm trying to say. Everything here follows from first principles. Okay, and then you can also now, so by the way, why there is not a third term? Why there is not a third term? Although there are 3 variables here, but I don't have a third term. Why? Well, the reason is that we are taking derivative with respect to y, and there is no dependence of z to y. This z and y are independent variables. So I cannot take derivative of this with respect to y. Okay, so from here we get that dg dy. Okay, so let me write it like this: df dx dg dy plus df dy. I mean, this is equal to minus df dy. And we just divide. So we get dg dy is equal to negative df dy over df dx. So that's the equation that we were looking for. As I said, if you know what you're doing and you don't run risk of making mistakes with notation, you can just completely forego with this g. And as I wrote at first, just write x equal to a function of y and z. So there would be x of y and z. And in that case, things become very simple. Here you would put the x, and then you calculate this easily, dx dy. You would get that dx dy is equal to this divided by. Okay, so this is, again, there is a nice check here that you can make sure that at least you haven't made a crazy mistake. The check here is that, again, in kind of simple-minded way, we just cancel. You get x over y, which is x over y. So formally, kind of makes sense, at least. Anyhow, so back to our problem now. So in the problem, I can just say, so it turns out that dx dy is equal to negative, well, df dy, of this guy with respect to y, it's 2x2 y z2 plus xz, right? Df dy divided by df dx, 2x y2 z2 plus yz. All right, plus yz. So the only simplification we can do is to cancel one factor of z. So this is equal to negative 2x2y z plus x divided by 2x y2 z plus y. So that's what we were looking for. So again, we use chain rule, but in a rather little bit different way. It's not very straightforward way of using chain rule. We use chain rule, but in this form, at least. So a similar way, we can just say similarly for dz, dx dz. So I don't compute it, but again, it's a quotient of two things. Dx dz is df dz divided by df dx. Okay, so once you know you're aware of notation you're using, more or less, after that follows mechanically, more or less. Any questions?
Could you explain how you got from the cloud step?
Talk a bit louder, please. What was the question? Sorry.
Sorry, can you explain how you got from the step before the cloud?
Oh, this equation?
Yeah.
Oh, yeah, this is nothing. This is just the definition of this function g of y and z. As I said, I could have just said that, well, this is like x, right? Without introducing an extra notation even. But if you are aware of the fact that x is a function of y and z, you can do this. You can just write this and then you don't have to do anything. This is your original equation, right? F of x, y, z equal to 0. I haven't done anything. I just differentiated on both sides with respect to y, with respect to z. And then I just said, well, I cannot forget the fact that x can be thought of y and z as a function of y and z. You can say y also can be thought of as a function of x and z also can be thought of as a function of x and y.
Okay, but can you explain how you got to the cloud from that step?
So how to get to the cloud?
Yeah. Yes.
Okay. Right. So what we are doing here, we are differentiating this function with respect to y and z. So now we are using chain rule. So we are using two facts. We are using the first fact that when you are replacing x by its functional value in terms of y and z, this function is equal to 0. So its derivative with respect to y and z is identically equal to 0, right? It has to be 0 because the function is 0. It's not even constant. The function is 0. So its derivative is equal to 0. But on the other hand, chain rule tells me how to compute this partial derivative with respect to y and z. Because that's what I discussed, right? I mean, this is a function of y and z. This is a function of y and z. This is also a function of y and z. Of course, what could be a bit confusing here is that these second and third factors are very easy functions of y and z. They are not actually crazy general functions. Y is itself a function of y and z is equal to itself. Z is also a function of y and z, but is equal to z. It's only the first one that's different. So let me now give you another example, which would maybe it will give you the better feeling of where this comes from. Yeah, I think that's a fair question, actually. Yeah. So imagine, I gave you a function of 3 variables like f of x, y, z again. Okay, so this is given. So remember, so this is exactly like our first example when we discussed chain rule, right? So I mean, in that case, we took a function of 2 variables, but that really doesn't matter. This is a function of 3 variables. Okay, now imagine also each of them are functions of 2 variables. X is equal to x of r theta, y is equal to y of r theta, and z is equal to z of r theta. Right? And don't think of what's the meaning of r and theta. It doesn't matter. R and theta are general variables for us, just notations. I don't want to use x prime, y prime, or some other notation. Just R and theta. Okay. When you sub into this, we get, so then now the question is, what is the FDR? So what is the FDR, right? Because, I mean, now after replacement, we have replaced x, y, z by r and theta. So we want to know what is the FDR. And that's exactly what chain rule tells us how to proceed, right? Chain rule tells us that, well, this is equal to df dx, dx dr, plus df dy, dy dr, plus df dz, dz dr. Are you happy with this so far?
Yep, makes sense.
So that's a general rule, right? That's what we discussed in first example. This is chain rule. This is chain rule. All right. So what I'm saying is that we are using the same rule here, except that it's such a simple case that it has become confusing. Indeed, it's rather confusing. So you have to kind of entangle the, it's not entangle, it's just, I would say, decipher the kind of simplicity of this problem to see what is going on. So let me tell you. Okay, there are two facts. Now, in general chain rule, we were not told that f of x, y, z is equal to 0. I mean, this was a general function. But here I know that this is equal to 0. And now x is equal to x of y and z. Y is equal to y of y and z. What is equal to y? It doesn't matter. This function is also is equal to y. That's fine. Z is equal to z of y and z. Is z. Do you see the logic here? I'm not using our theta variables. I'm using yz variables, but that's okay. I mean, we have the functional dependence here. We have the functional dependence here. And we have not the functional dependence for the first one, but we know that there is a functional dependence. Its exact form, it doesn't matter. We want to compute partial derivatives. And then all you have to do, you use just this formula. Okay, so let me call it a star. So a star, in this case, implies, well, what we have to do? We have to take df dx, dx dy. I mean, we are deriving this with respect to y and z now, right? Plus df dy, dy, plus df dz, dz dy. But again, this is equal to 0 no matter what. And you see what's going on. Dy dy is 1. Dz dy is 0. Why dz dy is 0? Because these are independent variables, right? These two variables are independent variables. So that's equal to 0. Okay, and that's exactly what, that exactly takes you to that cloud stuff that you ask this question. This was a very good question. Thanks for asking. I explained it in class when we were driving it, but I always said that, well, it follows from chain rule and follows from this. Maybe it was a bit fast, but now we have.
Okay, thank you.
So are you happy with this now? Are you getting it? It was a very good question. Indeed, you exactly did point out the crucial thing. It's always a matter of notation, but if you don't choose the notation or if you don't understand notation, things can go wrong or become confusing for no good reason, really. It shouldn't be. But thanks again for asking the question. Yeah. Excellent. Okay, so you guys should not hesitate to ask questions because I know you're able to ask good questions. Okay, so if there are no questions, let me now set another set of ideas, maybe. So another thing was, we discussed gradient and directional derivatives. So this was an important aspect also. So we discuss it now. So gradient and directional derivative. So these two concepts are tied together. I mean, they go hand in hand. Directional derivative is an important intuitive concept. A gradient is also geometric, but it's less intuitive. But let me start with gradient. So imagine you have a function of 2 variables or 3 variables, for example. So one thing we have to remember, as you know, is that gradient is always a vector. It's not a scalar, right? Gradient is a vector. So, and the notation for gradient was this. Also, we use grad. So remember, we use these two notations. And what is this? This is equal to fx, fy. It means partial derivative with respect to x, partial derivative with respect to y. In this case is partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. Okay, so it's a vector. And of course, in last section of this course, chapter 6, we said gradient is a vector field. So it was kind of elevated to a kind of totally different level of vector fields. But it's, at each point is this vector. And when you move from one point to another point, you get a field of vectors. It's called vector field, as you know. Anyhow, this is a vector. Now, the question really was, what is the meaning of this vector? I mean, why this kind of combination of partial derivatives like fx, fy, fz makes sense? What is it that it's trying to measure? What is it that it's trying to tell us? Of course, it's partial derivatives, so it kind of gives, each of them gives you a rate of change of f in x direction, in y direction, and in z direction. But the totality of them is a vector, right? So you get a vector now. So this is gradient of f. So what we want to know is, what is the geometric meaning of this vector? For example, what does the length of this vector or magnitude of this vector signifies? And what does its direction signifies? It's a vector, so it has a magnitude and it has a direction. Each of those things signal something about the function, right? So we have to understand that. So that's why we discussed the meaning of gradient. There are 2 ways to understand the meaning of gradients. The first one is, so let me ask the question then, what it means. Or what it measures. So these are the questions we want to ask, right? Okay. So the first answer is that, let us look at the level curve of f. Remember, we had this notion of level curves of f. So we just wrote f of x and y equal to some constant value. We got some curve, right? So this constant f is equal to, for example, 1 in this case. So Either you're so good you can draw it yourself without a computer aid, or you give it to your calculator or computer, and there are zillions of softwares calculate the level curves for free for you. And here comes this curve. Okay, what's the relation between this curve and gradient? Do you remember? So what happened is that at each point, gradient is orthogonal to this curve. So now, at each point, the gradient is orthogonal to your curve. Now, so at least the direction of the gradient vector is on the direction of the normal to the curve. The magnitude, I'm not saying anything about it right now, but this direction has a very, very clear geometric picture. It is orthogonal to the curve, level curve. So if you draw another level curve, to all these other level curves also, the gradient is orthogonal. So it's a very nice picture. The direction of the gradient is the normal to your level curve directions. Now, this is for functions of 2 variables, but we can have a function of 3 variables. In that case, level surfaces. So this is a level surface. And in that case, also, the gradient at each point is the normal line, normal vector to the to your level surface. So this is like f of x, y, z may be equal to 2. So this gives you a surface. At each point, your gradient is normal. At least as far as the direction goes, the gradient, we know that is normal to the level surface or level curve. The magnitude, as I said, we are going to discuss next, but just understand this. There is one case, though, that a gradient kind of doesn't have very precise or well-defined meaning, but in that case, it has a meaning on its own anyhow. And that's the case where gradient is equal to 0, right? So if gradient is equal to 0, I cannot say 0 vector is normal to this surface. So if gradient is equal to 0, it kind of loses its geometric meaning. So points where gradient is equal to 0 are kind of very special, very rather difficult, I wouldn't say singular, but critical points. And in fact, they are critical points of when you're maximizing, minimizing function. You go at the points where gradient is equal to 0, right? That's how we solve this thing. So I think these 2 pictures you should have in mind. For example, here's a nice example. I mean, let me put it like this: gradient of f at 1, 1, 1 for f of x, y, z equal to x2 plus y2 plus z2 minus 3. Oh, whatever, doesn't matter. Find gradient of f at 1, 1, 1 for f of x, y, z equal to x2 plus y2 plus z2. Well, okay, we know what the answer is. I mean, gradient of this function is very simple. It's equal to 2x, 2y, 2z. Gradient is very simple. It's 2x, 2y, 2z, right? By this rule, we know that gradient, it should be orthogonal to the level surface. And let's see if this is actually the case here or not. Let's see if this is the case. What is the level surface in this case? Can you give me the equation of the surface that I have to look at in this case? Well, the answer is easy. We have to sub in f of 1, 1, 1. If you sub in, you're going to get 3. So equation of your surface is x2 plus y2 plus z2 equal to 3. This is the equation that you have to take, right? So drawing this, of course, these are spheres. I mean, in this case, this is just a sphere of radius root 3. And what is the importance of this vector, 2x, 2y, 2z? Look, if you are at the point x, y, z on the surface, the normal to the sphere is exactly along this radial line. So if you're on a point on the sphere, this is what you know from geometry. If you're on the point of a sphere and you want to draw the normal line to the sphere, all you have to do is connect to the center and continue that line. Then you know that that line is normal. And that's exactly what this equation is telling. So this is okay. So at least we know that they all look like this. But now the question is, what is the magnitude of this guy? Well, let's look at the magnitude. Magnitude of this vector gradient is equal to twice square root of x2 plus y2 plus z2. Okay, but I know that x2 plus y2 plus z2 is equal to 3. This is equal to 2 root 3. Okay, so we found the magnitude of this vector. It's 2 root 3. But now the question is, what is the importance of this number, right? So, so unfortunately, we are over time. So we continue on Friday then. We just continue on Friday. Okay. Any questions? Okay, guys, have a good day. And then I see you on Friday. Yeah. Bye-bye now.